All right. Logarithm graphs. Now, a logarithm. Y equals log x. Don't forget, if there's no base, it's log 10, base 10, because our number system is base 10. If it's ln, the base is e, they really don't ask much about that. But, it works the same way. Different button on the calculator, so no big deal. Now, just to make this look more familiar for the acronym we have, when we use that BAE, if you remember that, base, answer, exponent, we got to keep this in mind as we think about a graph. If we take a look, what do I raise 10 to get x? The answer is y. So when we think about this, if we have a 10, a positive 10, over here in the negatives, if x is negative, is there any way to raise 10 to a number and get a negative answer? Now, just in case you forgot, negative exponents always meant reciprocal. Like if I raise 10 to the negative first, I get 1/10. 10 to, no matter how big we make that, well, 1e to the negative ninth means 1 times 10 to the negative ninth. Bad example. Let's try this. A number, it'll give us a numerical answer to 4. There we go. 0.001. The 1e to the negative ninth would be 0.0000000001. I mean, we're getting really close to 0. But no matter how negative I make that exponent, I'm never going to cross over to negatives over here. So for a logarithm graph, quadrants 2 and 3, there's nothing there. It's blank. Quadrants 2 and 3 are blank. Now, let's think about what I just said. And keep in mind that y is the exponent. When I had a negative exponent, I got a decimal. 0.1 is 1/10, so that's the same thing as a fraction. And that's what we talked about when we reviewed exponent rules for negative exponents when we were in this chapter with exponentials and logarithms. So when my exponent's negative, y is your exponent, x is the result, kinda. If I have a negative exponent, when y is negative, you're down beneath the x-axis, I get a fraction or a decimal less than a whole 1. And like we just showed, the more negative, so the further down you are, the more negative your exponent, the teenier and tinier your decimal is. So what happens is your graph in between 0 and 1, the graph is beneath the y-axis. And the further down you go, the closer and closer you'll get to 0, to the y-axis. Now, I had this cross here at 1, 0. Think about it. We said this. What is anything to the 0 power other than 0 to the 0 power? That's complicated. We don't want to get into that. Anything 0 power is 1. So remember, y is the exponent. So 0 high, you hit 1. So your x-intercept is at 1 for these graphs, no matter what the base is. Say this was log base 5. 5 to the 0, still 1. Say it was log base a trillion, still hit right there. Trillion to the 0 power, still is 1. Now, the further out we go, let's think about it. What this is saying is, what do I raise 10 to get wherever we are on the x-axis? And as we head over, well, there's no number right in our brains we can think of to raise 10 to get 2. So if you think the first whole numbers we're going to have is 10. 10 to the first is 10. Think about it. The very next whole number I'm going to have, and remember, this is y. This represents y. I'm not adding y into this equation here. The very next whole number I would get for y, 10 squared, is all the way at 100. So I'd have to go all the way out to 100 just to hit 2. And yeah, I mean, that's less if your base is smaller than 10. But for base 10, we'd have to go all the way out to 100. And let's say for base 6 even, we'd have to go all the way out to 36. 36 squared is 36. So the way this looks, you know, you're down here, you're shooting up from negative infinity close to the y-axis. You start heading over a little bit. You hit the x-axis at 1. And then you start going up, but it goes up very slowly. Now, even though it would take all the way to 100 to hit 2, it still is going up, but it's going up very slowly. And over here, no matter how far down we get, let's say we had like 10 to the negative 100th, all that is 1 over 10 to the 100th. 10 to the 100th would be a 1 with 100 zeros after it. I'm not going to write that out. We just get teenier and teenier and tinier and tinier. We get so close to 0, but we never hit it. And I mentioned this word a couple times before. If you have a graph where you get so close to a value, but you never hit it, it's called an asymptote. Now, for an unshifted logarithm graph, the asymptote is always going to be the y-axis, but just be careful. Y equals 0 is not a vertical line. We saw this the other day. A lot of people forgot that with that y equals half, I think, on a question. The y-axis is actually x equals 0, because everywhere on the y-axis has an x coordinate of 0. Now, another thing I want to mention here. To solve an exponential equation, we had to take the logarithm, because logs and exponentials are inverses. That's how we solved some of the exponential functions, by taking the logarithm. We could do that because they are inverses. So what happens is they'll say which one describes or which graph shows the inverse of, I don't know, y equals 2 to the x. So you think, hey, that's an exponential. If I take the inverse of that, it's a logarithm graph. And then you pick the one that's shaped like this. Just fill this sheet out as we go along. I'm going to do it for us here. Now, number one, and like this says, these are old Regents questions, so this is kind of what you should expect. The graph of y equals log x. Hey, I did it right here. I already said 2 and 3 are blank. It's in quadrant 1 and quadrant 4. Number 2, and the answer is this one right here. We're looking for the one that's false. I'll discuss that in 1 second. Let's go through the rest of the choices here. The graph has no y-intercept. I said asymptote means it gets so close, but it will never actually hit the y-axis. With our example here, even if you crank out a negative 100 way down as your exponent, you're not going to be 0. You're going to be so close to 0, but you're not actually going to be 0. This would be 1 over 10, or 1 with 100 zeros after it. So close, but it's not 0. The domain is x, range is y. Domain is the set of positive reals. Yeah, that's what we said right here. There's no negative x's, so positive reals, that makes sense. The range is a set of all real numbers. Range is y, and it goes all the way down forever and ever. And even though it goes up slowly, it's still going up. This is false because, like I said, the asymptote is the y-axis, which is x equals 0, not y equals 0. And that's why they asked this. Now, what's nice is a lot of the questions for this are either just something you can type into your graphing calculator, or it has to do with the shifts. And I've talked about this before, that you guys could have figured after we went over the rules some of the shifts out, even without ever learning the shape of the graph. 5 left, horizontal shift is in the parentheses, and it's backwards. So we got to be in the parentheses for a vertical shift. Normally, plus means right, like when we talk about positives on the x-axis. But when we talk shifts, translations, if you want to think about geometry, it's backwards. Inside is backwards. Inside. That's left. And this is right. Number 4, the graph of log base 2 of x is translated right 1 unit. That would be in with x in parentheses, and it's backwards. So that's x minus 1, down 1, minus 1 outside of it. So let's find the new x-intercept. Now, it's been a while since I had mentioned this, but you go to math, log base. So that's, you just hit math, and then go all the way down or hit up, log base. Oops. You got to be in y equals, though. Good job, me. There we go. Base 2, x minus 1, hit over minus 1 again. Let's check it out here. And this is what I was talking about. A lot of times, the questions they ask, you can just type right into your calculator. Coordinates of the x-intercept, 1, 2, 3. You don't even have to hit table. We can see it. Now 5, which sketch shows the inverse? Oh, there we go. So like I said, the inverse of an exponential is a logarithm. That's not the shape of a logarithm. That's not either. That's not what it looks like. This one is. The only one that looks like that. You don't even need to know what the base is. It can't be any of those other ones. Well, I suppose it could be this one if it was flipped over, but it doesn't say that. That's why this is here. We don't have to worry about that. Number 6, the cells of a particular organism increase logarithmically if G represents cell growth and H represents time in hours. Which graph best represents the growth pattern of the cells of this organism? All right. Now, if we take a look, this one's the only one that follows the shape. So we already know that's the answer. That's half a parabola. That's a linear. That's a linear. This is the one that makes sense. It's missing this right here because if we, excuse me here, G represents the growth. We can't have a negative growth. That would be decay. So since we're only modeling the increase, we can't have any of that. Can't have anything less than 0 if we're talking about increase. And hey, another Regents question where they're just asking you if you know the basic shape of this. Now, there's no negative out front, so it's not flipped over. It's got to be this one right here. Like I said, a lot of the questions on the Regents are either just, here's a logarithm, which one's the correct for a shift? Hey, that's nice. Right there. Or it's just something you could type into your calculator. Like this one mixed both. We had to know how they shift and then typed it in to get that right there. Now for the rest of the pack, you can just use your graphing calculator, go in and check them out, see what they look like. And tomorrow, we'll maybe talk about it a little bit. We'll work maybe the first half of class tomorrow, and then that's it.